Okay, welcome back to this next session, TA session number 11 in this course, Principles of Signals and Systems, offered by Professor Aditya Jagannatham from IIT Kanpur. My name is Yashvanth, and I'm presently a PhD student at EC Department, IISc Bangalore. And my research interests lie in signal processing and applications to wireless communications. Okay, so the topics that we will be covering for today includes discrete Fourier transforms. So recall that in the last class, last session, we studied about discrete time Fourier transform, which essentially is the Fourier representation of a discrete time signal. But the discrete time Fourier transform in the frequency domain is a continuous time domain signal, a continuous frequency domain signal. Right, so that was the story for discrete time Fourier transform. But discrete Fourier transform is another representation of the Fourier transform of a discrete time signal. But the frequency domain representation will also be discrete. Okay, that's the key difference between DTFT and DFT. In DTFT, the frequency domain signal is continuous, whereas in DFT, the frequency domain signal is also discrete. Like in both the cases, both DTFT and DFT are defined only for discrete time signals. Okay, so as usual, we will start with summarizing week number 11's lectures, and then we'll solve some problems. Okay, so of course, the first professor had solved some examples related to discrete Fourier series, discrete time Fourier transform, and discrete Fourier transform. So in particular, discrete Fourier transforms are essentially defined as is defined for a finite length sequence x of n. It should be a finite length. Okay, and for such kind of sequences, discrete Fourier transform is defined by this particular expression here. That is x of capital X of k equals summation n equal to 0 to n minus 1 x of n into e power minus j2 pi by n into small k into small n. Okay, and where this k is the frequency domain index, right? It's not a continuous variable, it's a discrete variable, because in DFT the frequency domain signal is also a discrete signal. Therefore the k only takes integer values, and this is also the number of values over which DFT is defined is also an n length signal. So if you take an n length time domain discrete time domain signal, its DFT is also an n length discrete frequency domain signal. So that's basically the first observation to make. And in particular, what we can do is we can, for notational simplicity, we will call the argument w e power minus j2 pi by n as wn. So wn essentially is what is called the twiddle factor. Okay, so it is only parameterized by the number n, capital N. Fine, this is called the twiddle factor. That's about discrete Fourier transform. So then the natural question is, what is inverse discrete Fourier transform? That is, if you have the knowledge of discrete Fourier transform, how will you recover back my discrete time domain signal? So that's basically inverse discrete Fourier transform. That is given by the time domain signal equals 1 by n summation k equal to 0 to capital N minus 1 x of k e power j 2 pi by n into km. Okay, where m is the index of the time at which you want to know the inverse discrete Fourier transform, and k is a frequency domain variable over which you are summing up your summation. Fine. So now basically, if you in the context of twiddle factor, this is also same as 1 by n summation k equal to 0 to capital N minus 1 x of k wn to the power minus km, because already j2 pi by n, but for twiddle factor you need minus, that's why there's a minus times I'm multiplying km. Okay, so twiddle factor power minus km. Okay. Now again, as we discussed, x of n and capital X of k, that is the time domain and frequency domain representation, both have identically n samples. And the relation between discrete Fourier series and discrete Fourier transform is as follows. Suppose if you construct, let's say, x of n in discrete Fourier transform, we only consider an x of n over, or for n is equal to 0 to some capital N. That's our number. N is something that we fix. Now suppose if you repeat this, x of n as a periodic version, then that becomes a discrete time periodic signal, for which you can always define the discrete Fourier series, right? And that's for the same signal you can also define discrete Fourier transform, because after all, although it's periodic, it's a discrete time signal. So if you compute a discrete Fourier series of that signal and the DFT of that signal, they are related by this expression. That is, the kth force frequency component times n, where n is the endpoint DFT you take, or the period of your discrete time signal, equals the DFT, the kth DFT coefficient. So this is the relation between the discrete Fourier series and discrete Fourier transform. Okay. Similarly, there's a relation between discrete time Fourier transform and discrete Fourier transform. What is that? Namely, that you take DTFT, you sample the continuous. That is basically DTFT is a continuous time domain signal, but in the frequency domain. Sorry, not time domain. It's a continuous frequency domain signal. You sample that signal at omega equal to 2 pi k by n. Okay, so you will get several distinct values of frequency domain sample. You collect all of those samples. That is basically your DFT. And by how much ever if you sample n samples within one, so recall that DTFT is a periodic signal in 2 pi, right? So within one period of DTFT, if you sample n times, if you take n samples, and that constitutes the n length or n sample DFT of the same discrete time signal, for which you basically uh, for which you have constructed your DFT. Okay, sampled version of DTFT equals DFT. Now, properties of DFT, right? So if you have a discrete time signal x of n, then let's say its DFT is x of k, then the following properties hold. A times x of n plus b times x2 of n has a DFT a times x1 of k plus b times x2 of k. That's called the linearity property of DFT. If I have capital X of n, right, that is, by what do I say? Basically, this is a duality property. That is, if I give the DFT as the what DFT that function as a time domain signal, then the corresponding DFT will be the DFT of that particular time domain signal will be n times x of minus k modulo n. Okay, this is basically what is called a duality property of DTFT. Similarly, you can define time shifting property. You can define frequency shifting property. In time shifting property, what it says is if you delay by a amount of m, you will also multiply a phase shift by that in the frequency domain. So this Wn is basically the twiddle factor that we just described above. By the way, this is taken from the reference Oppenheim table number 8.2. Okay, and convolution frequency shifting property, what it says is, suppose if you multiply by a complex exponential in a time domain, then your corresponding DFT will be delayed by L samples. Okay, now convolution property says that if you convolve two discrete time signals in the time domain, their corresponding DFTs will basically be multiplication in the frequency domain. Only one small difference. Note that this convolution is not the regular convolution. See, you see that it is n minus m modulo n. It is not just n minus m. This convolution is for circular convolution. Okay, this is different from the linear convolution that we have studied till now. Okay, so the only difference between circular convolution and linear convolution is you will apply a mod n. After you delay n minus m and apply a mod n to that. Okay, modulo n. So what does it mean? You divide n minus m by capital N, and whatever is the remainder, that will be the argument for x2 in the summation. Okay, that type of convolution is called circular convolution. Now, multiplication property says that if you multiply two time domain signals, the corresponding DFTs will be DFT. You will circularly do a circular convolution of the corresponding frequency domain signals. Now, conjugation says that if x conjugate of n will have the DFT capital X conjugate of minus k mod capital N. Okay. Similarly, you can go through the other aspects also. I have taken it from the Oppenheim book only. Okay. Again, famous Parseval's theorem says that if you sum over the energy in the time domain, and that is same as the energy in the frequency domain. So that's basically called the Parseval's theorem. And I've just written the duality property again, just to denote what this notation means. Minus k in subscript capital N. That means essentially you do minus k mod n. That's called a duality property. Okay, so these are basically the properties of DFT. And there's one more property. What you can always show is that the DFT matrix follows what is called the Hermitian matrix, Hermitian symmetric property. That is, H Hermitian H will be equal to identity matrix equal to H Hermitian. So this is basically the quick recap of what has been done in the class. Are there any questions still here? Are there any questions? Can you repeat the Hermitian property? Okay. So basically what I'm saying is, see, this H is basically what is called a DFT matrix. That is, it's an n by n DFT matrix. Okay, basically it's made up of twiddle factors. Okay, I think professor had discussed this in the class, right? Twiddle factors, you basically construct what is called DFT matrix, n by n matrix. You can show that that matrix follows the property H Hermitian H, which is equal to H Hermitian. That is, you first take the Hermitian, then multiply by H, or you first take the you multiply H and H, you pre-multiply, post-multiply H by H Hermitian. Both these matrices will be equal to identity matrix. If this satisfies, then you will base, okay, this is called the, oh, sorry. This Hermitian symmetry means H should be equal to H Hermitian. That is the Hermitian symmetry means. But H Hermitian equal to identity equal to H Hermitian H means it's the orthogonality property of DFT matrix. Yeah, thanks for catching that. Okay, so it follows Hermitian symmetry and this is basically unitary property. It's called unitary property. It's called a unitary matrix. You know, a matrix A is said to be unitary if A Hermitian equal to identity, or sorry, A Hermitian A equals identity. Both are same. It should satisfy both the properties. Then that's called a unitary property. Is it okay? H Hermitian equal to H means that is unitary Hermitian symmetric. Is it okay? I didn't understand your reply, but uh, but do you have any doubts? I'm not able to understand your reply. Okay, yeah, fine. So now let's start with the question problem solving for today. So basically, that what I mean, what we are going to do is see some problems on how to on related to DFT today. That's basically the goal for today. The first question is, let's say x of n equals sine pi by pi n by 2 or n pi by 2 for n equal to 0, 1, 2, 3. You just take 4 samples. Okay. And h of n is nothing but minus 1, 2, minus 3, 4. Okay. You see that there is an arrow mark here that indicates minus 1 is h of 0. Okay. H of 0 is minus 1. So to indicate, if I put an arrow mark, that means that corresponds to index at 0th time index. 2 is h of 1. H of 2 is minus 3. And h of 3 is plus 4. So that's basically the what? That's basically your h of n. The question is perform circular convolution of x of n and h of n, right? So basically, let's do the circular convolution. Let's say x of n. What is x of n? Sine n pi by 2, n equal to 0, 1, 2, 3. So basically, sine 0, sine pi by 2, sine pi, and sine 3 pi by 2. Fine. So basically, now sine 0 is nothing but 0. Sine pi by 2 is nothing but 1. Sine pi is 0. Sine 3 pi by 2 is again minus 1. Okay, now h of n is nothing but minus 1, 2, minus 3, 4. That's the given question. Okay, now circular convolution we need to do. Just apply the definition. That is y of n is summation over m equal to 0 to capital N minus 1 x of m into h of n minus m modulo n. Right? What is the n minus m modulo 4? Here n capital N is something but 4. Therefore, this is same as n minus m modulo 4. Okay, now let's do. Now you see, this is a 4-length sequence. This is another 4-length sequence. Circular convolution will always give same length sequence. So if you convolve two 4-length sequences, the circular convolution will also be a 4-length sequence. That is a property of circular convolution. Therefore, this y of n also we need to compute for 0, 1, 2, and 3. Because x of n is also from 0, 1, 2, 3. H of n is also from 0, 1, 2, 3. Therefore, y of n will also have the non-zero entries at 0, m equal to 0, 1, 2, 3 only. Therefore, we need to find just these for circular convolution values for these 4 values. So y of 0 at n equal to 0, y of 0 is nothing but so basically what I'm going to do is I'm going to expand this summation. Okay, there are four summations here, m equal to 0 to 3. So I will expand this as y of n equals x of 0 into h of n mod 4. That is when m equal to 0. When m equal to 1, then you get x of 1 into h of n minus 1 mod 4. When m equal to 2, you get x of 2 into h of n minus 2 mod 4. When m equal to 3, you get x of 3 into h of n minus 3 mod 4. Okay, therefore, now let's compute for at n equal to 0. Then one put n equal to 0 here, put n equal to 0 here, 0 here, and 0 here. Then what you get is x of 0 into h of 0 mod 4 plus x of 1 into h of minus 1 mod 4 plus x of 2 into h of minus 2 mod 4 plus x of 3 into h of minus 3 mod 4. Okay, now what is 0 mod 4? That is, you divide 0 by 4 and whatever is the remainder. But 0 by 4 is nothing but 0. It has no remainder. Therefore, 0 mod 4 is 0. So 0 mod 4, h of 0 mod 4 is h of 0. Now, what is h of minus 1 mod 4? I have written down here. Minus 1 mod 4 is same as minus 1 plus 4 mod 4. This is a property of modulo property, the remainder property. Right? So then my 4 minus 1 is what? 3. So 3 mod 4 is nothing but 3. Why? Because if I divide 4, but what do I mean by 3 mod 4? I take 3 and divide it by 4. What is the remainder? What is the remainder? Is 3, because only 0 times. You get 0 times 3 plus 3 is equal to 3. Sorry, 0 times 4 plus 3 equals 3. Right? That is basically a quotient remainder theorem or whatever is that. So the modulo remainder is what? 3. Therefore, minus 1 mod 4 is equal to 3. Similarly, if you do minus 2 mod 4 is same as minus 2 plus 4 mod 4, which is same as 2 mod 4 or equal to 2. Similarly, minus 3 mod 4 is nothing but minus 3 plus 4 mod 4. Minus 3 plus 4 is nothing but 1. So 1 mod 4 equal to 1. Okay, therefore what you have is that substitute minus 1 mod 4 with 3, substitute minus 2 mod 4 with 2, then minus 3 mod 4 with 1. Then what you get is x of 0 h of 0 plus x of 1 into h of 3 plus x of 2 into h of 2 plus x of 3 into h of 1. Now that's all. We just need to substitute all the values. You see, we know x of 0 is 1, x of 1 is 1, sorry, x of 0 is 0, x of 1 is 1, x of 2 is 0, x of 3 is minus 1. Similarly, h of 0 is minus 1, h of 1 is 2, h of 2 is minus 3, h of 3 is plus 4. Just substitute for these values in this expression. In this expression here, you can show that it is 0 plus 4 plus 0 minus 2, which is equal to 4 minus 2 equal to 2. Therefore, y of 0 is equal to 2. Similarly, if I want y of 1, then what I do is I'll put n equal to 1 here. Put 1 mod 4. So 1 minus 1 is 0 mod 4. Then 1 minus 2 is minus 1 mod 4. And again, this will be 1. So this will be minus 2 mod 4. Again, use these properties in this above equation. Okay, then you can show that y of 1 will be x of 0 into h1 plus x of 1 into x of 0 plus x of 2 into h of 3 plus x of 3 into h of 2. Okay, just again substitute for the values. You can show that the answer will come out to be 3 minus 1. Then it should be 2, not 3. Okay, fine. That is for y of 1. Similarly, if you compute for y of 2, right, you can again put n equal to 2 here. Where? Here. Put n equal to 2 here. You will get an expression. And again, use these properties of modulo property, and you can show that y of 2 will come out to be 2 minus 4 equals minus 2. Okay. Then y of 3, you can again similarly show, put n equal to 3 here. Here put n equals 3. And what you will get is y of 3 equal to minus 2. Therefore, you got y of 0 equal to 2, y of 1 equal to 2, y of 2 equal to minus 2, and y of 3 equal to minus 2. Therefore, your y of n is 2. Okay, this is maybe 2 because we made the correction. This may be 2. Then you have minus 2, and put an arrow mark to indicate that this 2 is nothing but y of 0. Okay, so this is the final answer. Is it clear? Okay, great. In fact, I'm going to give a short trick now, which you can always use. So if I want to convolve any circular, do a circular convolution between two n-length sequences x of n and h of n. That is, if I want to find y of n equal to x of n and y of n equal to circular convolution of x of n and h of n, then essentially what I need to do is I first stack y of n. I can obtain by just this matrix vector multiplication. What you do is that you basically, the first column of your matrix, you arrange with all the sequence of h of 0, h of 1, and so on till h of n minus 2 and h of n minus 1. Okay. The second column, you shift it by 1 unit. So shift everything by 1 unit down. So h of 0 will become the second place. H of 1 will come to the third place. So last place will be h of n minus 2. Then the h of n minus 1, you bring it to the first place. H of n minus 1 here. Now third column will be again do the same thing over the circularly shift the second column down by 1 unit. So that means h of 0 will come to the third place, h of 1 will come to fourth place, h of n minus 3 will come to the last place, h of n minus 2 take it to the bottom top again. So the third column becomes h of n minus 2, n minus 1, 0, 1, 2, 3, and so on till n minus 3. Okay. Similarly, you can keep on doing this n times. The last column will be such that the h of 0 would have come at the last element and h of 1 will start from the top. H of 1, 2, 3, and so on till n minus 1, and then you will have h of 0. You construct a matrix like this. Okay. And multiply this matrix with your x vector comprising x0, x1, and so on till xn minus 1. Okay, so this is an n by n matrix and this is a n cross 1 vector. Therefore, when you multiply a matrix by vector, you will get a vector of again size n cross 1. And the resultant vector will be the circularly convolved vector y of 0, y of 1, and so on till y of n minus 1. Okay, so this is the one shot, just you construct this matrix, multiply this with this vector. At one shot, you will get the entire circular convolution answer as a LHS. Okay, this is one short trick to do a circular convolution, which with very less time. Is it clear? Is the process clear? Hello? Okay, great. Let's move on. Second question is as follows. Let x of n be this sequence here. Okay, that is 4, 5, 4, 5, 4, 5, 4, 5. Question is simple. What is the discrete Fourier transform of the sequence x of n? Okay, solution. Okay, let me do one thing before that. Let me erase this so that it doesn't create any confusion. Okay. So the question is to find DFT of this x of n. So what you can do is that you can, this is a definition of your DFT. X of k equals summation n equal to 0 to capital N minus 1, x of n into e power minus j 2 pi by capital N into kn. Right here, what is n? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 lengths. So 8 length sequence, therefore n equal to 8. Therefore, you get 2 pi by 8, which is nothing but pi by 4. Okay, now what should we do? Now put sub x of n. I know the zeroth value is 4, x of 1 is 5, x of 2 is 4, x of 3 is 5, and so on. Therefore, use these x of n and this, and you can expand this to be this number here. Okay, that is x of 0 is nothing but 4, but e power 0 becomes 0, 1, therefore it is just 4. The second term will be x of 1 into e power minus j pi by 4 uh, uh, k into 1. There's a small mistake, I guess. Just a minute. Yeah. So it is all everywhere. It's not k. It should be. It should not n. It is k. Okay. You see, the second term is what? For second term is x of 1 into e power minus j pi by 4 k into 1. Right? It's just e power minus j pi by 4 k. That is basically this term. And x of 1 is nothing but 5. Therefore, that 5 will be coming here. The third term is what? X of 2 into e power minus j pi by 4 k into 2. Right? That is what I wrote here. E power minus j 2 pi by 4 into k, and times x of 2 is 4 because x of 2 in the given question is 4. Like that, you keep on filling up. This is x of 3 into e power minus j pi by 4 3k, x of plus x of 4 into e power minus j pi by 4 4k and so on. Okay, like that you need to do for all the 8 terms. There are 8 terms here. Okay. Now what I will do, I will use some property. Your e power minus j pi 5 pi by 4k, you can write it as e power minus j pi into e power minus j pi by 4k. That is, but e power minus j pi is minus 1. Therefore, this same as minus 1 into e power minus j pi by 4k. Okay, so that's why minus here is there. Similarly, you can write e power minus j 3 pi by 4k as e power minus j pi plus j pi by 4k, which is nothing but minus e power, which is nothing but minus e power j pi by 4k. Similarly, you can write e power minus j 7 pi by 4k as e power minus j 2 pi plus j pi by 4k, but by e power minus j 2 pi is equal to 1. Therefore, it is 1 into e power plus j pi by 4k. Similarly, e power minus j 6 pi by 4k is equal to e power minus j 2 pi plus j pi 2 pi by k, 2 pi by 4 into k. Okay, so that is nothing but e power plus j pi by 2 k. Now what I will do is I will use all these expressions minus pi by 4k, 5 pi by 4k, minus 3 pi by 4k, minus 7 pi by 4k, minus 6 pi by 4k in this big expression here. Right, you see here, right? Minus 5 pi by 4k you have, minus 6 pi by 4k you have, 3 pi by 4, 7 pi by 4, you have all these expressions. Okay, substitute for all these simplifications in the above equation 1. Okay, what you can show is they will all nicely cancel out with each other. You can show that, just simplify, nothing else. Okay, what you can show is your x of k will be equal to 4 plus 5 minus 5 into e power minus j pi by 4k plus 4 into e power minus j pi by 2k plus e power j pi by 2k plus 5 minus 5, that is 0, into whatever, doesn't matter because anyways is going to 0. Last term is 4 into e power minus j 4 pi by 4 into k. Okay, so this is just k. So again you can simplify that as this 4 is as 4. Okay, now this is again, you see this. Okay, maybe there is something again missing something. Yeah, nothing. We are not missing anything. Now what I will do is I'll multiply this by 2 and divide by 2. That's what I'm doing here. Okay, and this e power minus j 4 pi by j pi k will be as this because 4 and 4 get cancelled. Now what is this? This is nothing but Euler's relation for cos theta. Therefore, this is nothing but cos pi by 2k. This is exactly cos pi by 2k. 4 into 2 is 8, and plus e power minus j pi k is nothing but minus 1 power k, because e power minus j into whole power k, but e power minus j pi is minus 1, therefore minus 1 power k into 4. Okay, so this is a final expression for DFT. We just did simple manipulate. We applied the definition of DFT and we just simplified it. We did not do anything else. Is the solution approach clear? You can try on your own also. Just try to simplify and see if you are also able to do it. Is the approach clear? Okay, very good. Now let's move to the third question. Third question is compute the n point DFT of the following 4 signals. X1 of n is delta of n, that is your usual impulse function. Second is x2 of n, which is delta of n minus n naught, where n naught is some number between 0 and capital N. X3 of n is alpha power n, where again n ranges from 0 to capital N. And x4 of n is u of n minus u of n minus n naught, where u of n is the standard unit step function. Okay, and basically n naught can range between 0 and n. These are the four signals for which we need to compute the DFT. Fine. So the first we'll do it step by step. X1 of n is delta of n. So again, what is the DFT? X1 of capital X1 of k is nothing but sum over n equal to 0 to capital N minus 1 delta of n into e power minus j 2 pi by n into 2 pi by capital N into kn. So this is basically your definition for DFT. Now what happens is you apply this is an impulse function, so apply shifting property of impulse function. So only at you are this is nothing but delta of 0 into e power minus j 2 pi by capital N into 0 into capital 0 into k. It's 0 into k, because the summation is over n. Only at n equal to 0 the delta function will take the non-zero value. Therefore it is same as just the value delta of 0 into the function evaluated at n equal to 0. Only the first term of the summation will have non-zero value. But e power 0 becomes 1. Therefore, delta of 0, which is equal to 1. Therefore, what we saw is that if your time domain signal is a delta function, then your for DFT is a all one sequence from capital N is equal to 0 to capital N. It's not k minus 1. It is capital N minus 1. Okay, because DFT we only compute for a finite samples. Okay, is it clear? All right. The next question is x2 of n is delta of n minus n naught. Basically the same approach. What you will do is you apply the definition of for DFT, which is x2 of k equals sum over small n equal to 0 to n minus 1 delta of n minus n naught into e power minus j 2 pi by capital N into kn. But apply again shifting property, only at n equal to n naught will this term be non-zero. Therefore, you can show that this is equal to delta of n minus n naught into e power minus j 2 pi by n into kn naught. But delta of n minus n naught is 1 whenever it is we are at n naught. Therefore, it is just equal to second term. Okay. So basically what it says is that your x2 of k will be equal to this particular number here. Okay, or you recall that your e power minus j 2 pi by n was a twiddle factor, so you can write x2 of k as twiddle factor power n naught k, where k ranges from 0 to k 0 to all the way till n minus 1. Is it clear? All right. Third question. X3 of n is given to be alpha power n. What is its corresponding DFT? So then you can show that DFT is equal to summation over n equal to 0 to n minus 1 alpha power n into e power minus j 2 pi by capital K into small k into n. Now, so therefore your now what I will do is this 2 pi by, sorry, not I don't know why I'm using k everywhere. It is capital N, not k. Okay, so now what is this e power minus j 2 pi by n? That is a bit twiddle factor wn. Okay, power nk. Okay, so I can compactly write this as alpha power n into twiddle factor power nk, or I can write this as summation over alpha times twiddle factor power k the whole power n. Okay, because n is common to both the terms, so I will take alpha and w twiddle factor power k and take whole power k small n. Now this is nothing but geometric series because I'm summing over several n, alpha wn power k the whole power n. So it's a finite geometric series. So the closed form solution is given by this expression here, right? That is 1 minus alpha into wn power k whole power n divided by 1 minus alpha wn power k. Here the common ratio is alpha into wn power k. Right. Now therefore basically what you can, basically that's all. This is what is the solution. Your DFT is nothing but 1 minus alpha into twiddle factor power k the whole power n divided by 1 minus alpha into twiddle factor power k, where twiddle factor itself has this particular structure. Where is it? This, namely that it is e power minus j 2 pi by capital N. And k ranges from 0 to n minus 1. Okay, that's all. You cannot simplify this more. Is it okay? All right. The last question is x4 of n, which is equal to u of n minus u of n minus n naught, where n naught is some integer. That means what? You can show the u of n is a unit step function. From n equal to 0, it will be 1. And u of n minus n naught is something, but again unit step function, but starting at n naught only. Okay, therefore, if you subtract both the function, you will basically get 1 when n ranges from 0 to n naught minus 1. And so basically this difference is nothing but is the signal 1 if n lies between 0 and n naught minus 1, else it takes the value 0. Fine, that's basically your x4 of n. Now basically now we need to take the DFT for this function. Okay, so now what I will do, I'll put x4 basically what I will do is use the formula for DFT, that is summation over n equal to 0 to n naught minus 1 into twiddle factor power kn, and that is again as a finite geometric series, so you can write this as 1 minus wn power kn naught divided by 1 minus wn power k. Okay, now you can do this one, you can slightly even more simplify. What I will do is I will take wn power k n naught by 2 common in numerator, and I will take wn power just k by 2 common in denominator. So if I take wn power k and not by 2 common in numerator, I need to multiply the first term with wn power minus k and not by 2, so that both of them will cancel to give just 1. And the second term will be wn power plus k and not by 2, so that when I multiply wn power k and not by 2 into wn power k and not by 2, I will get wn power k and not. Okay, so that's basically the how numerator is changes. Now in denominator, if you take wn power k by 2 as common, then that is common. Then the first term, the 1, instead of 1, it should be wn power minus k by 2. So only then if you multiply two twiddle factors, that is here twiddle factor power k by 2 and twiddle factor power minus k by 2, both of them will give just 1 because the exponents will exactly cancel each other. And if you look at the second term, it should be wn power k by 2. So when you multiply wn power k by 2 with itself, you will get wn power k because exponents just add up. Okay, so therefore this expression is same as this expression. Okay, but now what you can show is that after all, this is e power j theta, some for some theta. This is e power minus j theta. Similarly, this is e power j phi, and this is e power minus j phi for some phi. Right, so it is basically subtraction of two complex exponential. So you can again write this as sine of n naught pi k by n divided by sine of pi k by capital N. And this again you can subtract the exponentials to get, basically it is a one twiddle factor divided by another twiddle factor. So it is the twiddle factor power k by 2 into n naught minus 1. That is, you subtract both the k n naught by 2 minus k by 2, which is nothing but k by 2 into n naught minus 1. Okay, so that's basically the expression for your DFT. Is it clear? Okay, very good. It's clear. Okay, let's move to the next question, which basically computes the inverse discrete Fourier transform of the signal of basically a given frequency domain signal. In fact, you're asked to find 10-point inverse DFT. Okay, that means you should have a 10 length DFT signal itself. So the given signal is x of k takes a value 3 if k equal to 0, and it takes a value 1 when k lies between 1 and 9. Okay, so clearly it's a 10-point signal in the frequency domain, with the first sample being 3, the rest of the samples being 1. Okay, we need to find the inverse DFT of this signal. So basically, first what I will do is I will recognize that this has a very nice structure. So can I write x of k equal to 1 plus 2 into delta of k? That's because when when k ranges from 0 to 9. That's because when k equal to 0, delta of k will be equal to 1. So x of k will be 1 plus 2, which is equal to 3. However, when k equal to 1 to 9, delta of k will be equal to 0. So the 2 in delta of k will also be 0. So x of k is just equal to 1. Therefore, this description that x of k takes a value 3 if k equal to 0 and it takes a value 1 when k takes between 1 and 9 can be written as 1 plus 2 into delta of k. Is it clear? First, this is the first step, very important step. Is this clear? Okay, I hope this is clear. Fine. Now, then the question is, now we just need to find the inverse discrete Fourier transform for this. That's all. So basically by linearity property, then your inverse DFT x of n is nothing but IDFT of 1 plus IDF 2 into, you can maybe take 2 outside also, 2 into IDFT of delta of k. That is all we need to find. Okay. Now IDFT of 1 is what? Delta of n. Why? Because that's what we proved in the previous question. You see, for delta of n, its IDFT is all 1 from 0 to n minus 1. And that's what we also have here. We have 1 from k equal to 0 to 9. Therefore, within this n equal to 0 to, from n equal to 0 to 9, your IDFT is something by delta of n, just from the previous question. Now, how about IDFT of delta of k? Okay, you will apply duality property, namely that what we saw, let small y of n be delta of n. Then from the previous question we saw that its DFT will be equal to 1. Now let's say that in the time domain sequence was equal to 1, then by duality property the DFT will be n times delta of y minus k modulo n. Correct? That's basically the duality property of discrete Fourier transform. Now, what is y of minus k? That is y of minus k delta of minus k. So n times delta of minus k modulo n. But delta function is an even function, so it is same as n times delta of k. Okay, so basically we have applied the duality property. Or in other words, what it means, it just means that one has the discrete Fourier transform n times delta of k, or 1 by n has the discrete Fourier transform delta of k, or 2 by n has the discrete Fourier transform 2 into delta of k. You see, 2 into delta of k is what we wanted, and now we got the answer. Therefore, IDFT of 2 into delta of k is nothing but 2 by capital N. Is it clear? Is it clear? Hello? Okay, fine. So it's clear. So therefore, now what is n here? N, we tell it's a 10-point DFT, right? So therefore, capital N is nothing but 10. Therefore, 2 by 10 is nothing but 1 by 5. Therefore, your IDFT of 2 into delta of k is nothing but 1 by 5. Therefore, by IDFT of 1 was delta direct, just a delta function, and IDFT of 2 into delta of k is 1 by 5. Therefore, your inverse DFT is nothing but x of n equals delta of n plus 1 by 5. Is it okay? That's all. This is basically the final answer. Okay, great. Now let's look at the next question. Next question is, find the endpoint discrete Fourier transform of your signal x of n equal to 4 plus cos square 2 pi small n by capital N, where n ranges from 0 to n minus 1, capital N minus 1. Very again straightforward. Okay, so first of all, apply the Euler's equation over cos, that is e power j 2 pi by capital N into n plus e power minus j 2 pi by capital N into small n divided by 2, the whole square. Because you have cos square, therefore you need to square this term. And now expand it using a plus b whole square. So 1 by 2 square, bring it common, so that is 1 by 4 here. So what you have is the first a square is nothing but e power j 4 pi by capital N into n plus e power minus j 4 pi by capital N into n plus 2. That's because the last term will have 2 into e power j 2 pi n by capital N into e power minus j 2 pi n by capital N. Both will cancel with each other, so it will only give you 2. 2ab part of a plus b the whole square. Okay, now simple. What I will do is that I will just expand it. 1 by 4 into e power minus j 4 pi n by capital N plus I have 2 by 4, right? 2 by 4 is nothing but half. So half plus another 4 is there. So half plus 4 is nothing but 9 by 2. That's what I wrote, 9 by 2. And the third term is 1 by 4 into e power j 4 pi by n into small n. Okay. Now this e power minus j 4 pi n by capital N can be written as e power minus j 4 pi by n into 4 pi by capital N into n into e power j 2 pi, because e power j 2 pi is anyways 1. So I'm just multiplying by 1. There is no problem with that. So now basically exponents will get added up. So it is same as e power j 2 pi by n into n minus 2 into small n. So for example, you can show that if you look at the first term here, it becomes 2 pi by n into n small n into j, right? Which is nothing but n cancel. And okay, this is basically, I can put another small n here. There is no problem. That's because e power j 2 pi by n is also equal to 1 for any integer n, small n. Okay, so you can write this number as this. Okay, therefore it is same as writing 9 by 2 plus 1 by 4 into 2 pi by capital N into 2n plus 1 by 4 into 2 pi by capital N into n minus 2 into n. That's because I have written this minus j 4 pi by n as 2 pi by n into n minus 2n. Okay, now that's all. This is basically the given signal x of n. What I just simplified 4 plus cos square 2 pi by n by capital N as the given in equation 1. Now recall the definition of DFT, which is given in equation 2. That is x of n is equal to 1 by n summation over k equal to 0 to n minus 1 x of k into e power j 2 pi by capital N into small k into small n. Now all you need to do is compare equation 1 and 2, just like how we did Fourier series and Fourier transforms in our continuous time domain signal. You just compare the exponential terms, right? The coefficient of exponential terms. Now what is capital N? Capital N is nothing but, okay, capital N is just capital N. So capital N here, capital N. Okay, so you just compare both 1 and 2, or you can show that at k equal to 0, that is correspond to n by 2. Okay, at k equal to 0, this e power 0 will be equal to 1. Therefore, you will have x of k by capital N. That is independent of complex exponential. So that must be equal to the constant in equation 1. Therefore, x of k by capital N is equal to 9 by 2, or x of k is equal to 9 by 2 into capital N. Now, when small k equal to 2, then what happens is you put k equal to 2 here. Therefore, it becomes x of 2 into e power j 2 by 2 pi by capital N into 2n. You see, this is an exact complex exponential that appears in the complex exponential in the first equation also. Therefore, the coefficient of this a complex exponential with namely x of 2 by capital N, because there is 1 by n outside. So x of 2 by capital N should be equal to 1 by 4 from equation 1. That's what I'm doing here. X of 2 for when k equal to 2, x of 2 by n is equal to 1 by 4, or x of k is equal to n by 4. Similarly, when a capital K is equal to n minus 2, you can show that x of k by n equal to 1 by 4, because that is from the third term of equation 1. So you can have x of k is equal to n by 4 again. Therefore, if you summarize, in fact, you don't have any other complex exponential in first equation. Therefore, for any other k, x of k by n is equal to 0. Therefore, x of k is also equal to 0. Therefore, if you summarize, your DFT x of k is 9 by 2 into n if k equal to 0. If k is equal to 2 or capital N minus 2, your DFT is equal to n by 4. Whenever k takes any other value between any other value except 0, 2 or n minus 2, it takes the value 0. So this is your final expression for DFT. Is it clear? All right. Very good. Okay, so I think let's we are exactly at the halfway of the lecture. What we will do is we will take a break, maybe till 7:10, and then again we will continue. Okay, please stay online. We will take a break till 7:10. Okay. Are you able to hear me and see my screen well? I've reshared my screen. Is everything okay? Okay. Let's continue with the next question, which is basically that you're given a finite sequence x of n, which is given as delta of n plus 2 into delta of n minus 5. Okay, this is your time domain signal, discrete time domain signal. Question is find the 10-point DFT of x of n. That is the first question. Second question is find the sequence that has a DFT of y of k equal to e power plus j 2 pi by 10 into 2k into x of k. That is basically what it's saying is find the inverse discrete Fourier transform of y of k, which is a phase shifted version of x of k. X of k is a DFT obtained in part 1. You multiply the x of k obtained in part 1 by e power plus j 2 pi by 10 into 2k. You will get y of k and take the IDFT of y of k. That is the answer for second question. This is basically the question. Let's solve it. So basically x of n equals delta of n plus 2 into delta of n minus 5. So what is the definition of DFT? X of k equal to summation n equal to 0 to capital N minus 1 x of n into e power minus j 2 pi by capital K into kn. Okay, again, yeah. Okay, so basically k or n, k equal to n, right? It's not n. It's basically say n. Fine. Basically, now what is x of n? You can put a delta of n into 2 in delta of n minus 2 in delta of n minus 5. So you will have two summations because you have two components in x of n. First is over delta of n into the twiddle factor power small k into n plus 2 into summation over n equal to 0 to n minus 1 delta of n minus 5 into twiddle factor power small k n. Now, by again shifting property of the impulse function, it is only at n equal to 0, this will non-zero value. But at that point, e power 0 will be equal to 1. Therefore, the first summation is just equal to 1. And second summation by shifting property, only at n equal to 5, this summation will have a non-zero value. At n equal to 5, this exponential become e power minus j 2 pi by n into 5k. And that multiplied by 2. Okay. Now, what is n? 10, because they've asked to find 10-point DFT. Therefore, capital N is equal to 10. Therefore, 2 pi by 5 is nothing but 2 pi by 10 is pi by 5 into 5k, which is nothing but 1 plus 2 into e power minus j pi k, because 5 and 5 get cancelled. But e power minus j pi is nothing but minus 1. Therefore, whole power k. Therefore, 10-point DFT of x of n equal to delta of n plus 2 into delta of n minus 5 is 1 plus 2 into minus 1 power small k, where k ranges from 0 to 9 because it's 10 points, so n minus 1 is 9. Okay, so this is basically the 10-point DFT. Maybe let me write it. K equal to 0, 1 and so on till 9. Is it clear? Okay, the next question is you take this x of what is the question? You basically multiply by e power phase shift in the to x of k and get y of k. What is IDFT of this? Now by time shifting property, we know that if you the y of n is given by an advanced version n plus 2 but modulo 10. Okay, why? Because what happens is that if I do x of n minus n naught, then it's corresponding in your frequency domain, it gets multiplied by e power minus j 2 pi by k into n naught, 2 pi by n into n naught, right? Now you see n naught should be minus 2. Only then minus here and minus here will cancel with each other and you will get plus j 2 pi by 10 into 2k. Right? Therefore, your n naught is minus 2. Therefore, it is nothing but x of n plus 2 in mod 10. That is, n naught is minus 2, right? Therefore, n of minus 2 becomes n plus 2 mod 10. Therefore, essentially, your y of n is nothing but an advanced version of your x of n modulo 10. Okay. Therefore, that is nothing but what is your x of n? X of n is nothing but delta of n plus 2 into delta of n minus 5. Therefore, what you should do? You should do x of n plus 2. Therefore, mod 10. Therefore, your y of n is nothing but delta of n plus 2 mod 10 plus 2 into delta of n plus 2 minus 5 mod 10. Why minus 5? That's because that is given in the question, delta of n minus 5. Fine. Now, what is n plus 2 mod 10? Okay. This I wrote it as n minus eta. Right, right. Okay, this one it's just this much. Okay, the second step is clear, right? So there's nothing but n minus 3, and this is over n is equal to 0 to n 9, right? 9. Okay, n plus 2 mod 10 is same as n minus 8. There is no doubt with that because essentially you can always write n plus 2 minus 10 mod 10. Okay, both are same. Can because this is a property of mod, so there's nothing but delta of n minus 8. This is needed. Just this is enough. Oops, sorry. Just this expression is enough. Okay, this is enough because unless you know the exact value of n, you don't know how should you do which property of modulus can you apply. Okay, so this is the answer. Is it okay? Is the solution here? This okay? This is enough. This is the final answer. Okay or not? Okay. Next question, interesting question actually. X of n is a discrete time domain signal given by 4 delta of n plus 3 into delta of n minus 1 plus 2 into delta of n minus 2, okay, plus delta of n minus 3. Okay, so this is basically the given signal x of n. Now, basically x of k is basically is a 6-point DFT of small x of n. That is the given. That is basically the given fact in the question. 6-point DFT. Okay. The question is find the finite length sequence y of n that has a 6-point DFT y of k equal to e power minus j 2 pi by 6 into 4k into x of k. It is same as previous question. Same question. That is what you do. You're just multiplying x of k with some complex exponential term, and that gives y of k. Find the inverse discrete Fourier transform of this. That is the answer to part A, 7a. Same. You should use time shifting property. Second question is find the finite length sequence w of n that has a 6-point DFT equal to real part of x of k. That is w of k is equal to real part of x of k. You need to find the inverse discrete Fourier transform of w of k. We'll do it, okay, systematically just by using the properties of discrete Fourier transform. First question, as I told, just use the time shifting property. By time shifting property, what are you doing? You're delaying by an amount of 4. Correct, because this is basically 2 pi by n, where n is the number of points of DFT, which is 6 point here. Therefore, you're relying by n not equal to 4. Therefore, this is same as your y of n is equal to x of n minus 4 mod 6. Do you agree? N not equal to 4. Is this okay? Yeah. Now, basically, what is x of n? 4 in delta of n, 3 into delta of n minus 1, 2 in delta of n minus 2, delta of n minus 3. But now you need to do operation of n minus 4 mod 6. That's all. So basically, what you do is that 4 into delta of n minus 4 mod 6, 3 into delta of n minus 5 mod 6, 2 into delta of n minus 6 mod 6. But n minus 6 mod 6 is the same as delta of n. Okay, because anyways, if you have n, if you subtract by 6 and take remainder with respect to 6, it is same as delta of n. Okay. Similarly, delta of n minus 3 minus 4 mod 6, but that is about n minus 7 mod 6, that is same as delta of n minus 1. Because delta of n minus 7 mod 6 is same as delta of n minus 7 plus 6 mod 6. Property of modulus. Minus 7 plus 6 is minus 1. Therefore, it's n minus 1. Delta of n minus 1 mod 6. N minus 1. That is enough. Therefore, your answer is 4 into delta of n minus 4 plus 3 into delta of n minus 5 plus 2 into delta of n plus delta of n minus 1. That is the answer for A part. Now, B part. You are asked to find the inverse for the DFT of real part of x of k. But real part of x of k is nothing but x of k plus x conjugate of k divided by 2. Therefore, W of n, which is the IDFT of real part of x of k, is same as IDFT of x of k plus IDFT of x conjugate of k whole divided by 2. But what is IDFT of x of k? X of n, small x of n. But we don't know the IDFT of x conjugate of k. That is what we will do next. IDFT of x conjugate k. What is it? Simple. It's not very difficult. Just use the definition of IDFT. Definition x of k is nothing but summation n is equal to 0 to capital N minus 1 x of n into e power minus j 2 pi by capital N into kn. Now take conjugation on both sides. Then what happens? X conjugate of k is nothing but summation over n x of n. Why? Because x of n is real. You see, x of n, this is all real signal. It doesn't take a complex value. Therefore, it doesn't matter whether you take conjugate for x of n or not. It will remain the same. Therefore, x conjugate of n is same. Yeah, actually, I have not removed it, but it's okay. Here, I will just I will. In fact, for this question, x conjugate of n is same as x of n. So it really doesn't matter whether you put conjugation or not. It's going to be same value. Okay. Therefore, what you will get is summation over n x conjugate of n into e power plus j 2 pi by n into kn. Okay, because minus becomes plus because you have taken the whole conjugation on both sides. But now you see this becomes plus, right? Now again I need to bring somehow minus. How do I bring? This is nothing but into 1, but 1 can be written as e power minus j 2 pi. Why? Because this is nothing but, this is nothing but, this is nothing cos minus 2 pi plus j sine minus 2 pi. But sine 2 pi is 0, cos minus 2 pi is 1. Therefore, you can just multiply this number by e power minus j 2 pi. There it won't change the answer because anyways it is equal to 1. But now you're multiplying two complex exponentials, so the exponents will add up. So what you will get is summation over n x conjugate of n into e power minus j 2 pi by capital N into capital N minus n. Why? Because it does this minus j 2 pi doesn't have capital N. Therefore, into multiply and divide by capital N. Okay, so that this n and n get cancelled, you'll get the second term here. The second, this 2 pi by capital N into minus n will be the first term here. Okay, into k. Now what I will do, I'll do a variable substitution. N dash is defined as n minus n into mod n. Okay, it's a variable substitution. So you can show that this expression under this new n dash variable will become this summation here. Summation n dash is equal to 0 to capital N minus 1. X conjugate of n is replaced by, because if you have n dash is equal to n minus n, then n is nothing but n minus n dash mod n. Right. So n is replaced by n minus n dash mod n into e power minus j 2 pi by n dash k, because is n minus n is nothing but n dash. Fine. Now what is this? Oops, sorry again. What is this? This is exactly nothing but the DTFT of x conjugate of n minus n mod capital N. Therefore, but what is the left hand side? Left hand side was x conjugate of k, because that's where everything started. We took the conjugate on both sides and then we did the simplification. Therefore, what we see is that IDFT of capital X conjugate of k is nothing but small x conjugate of n minus n mod capital N. Okay, therefore, this is equation 2. Put this in this equation. Which equation? This equation. Because I now find the IDFT of x conjugate of k. So if you put that equation, you will get W of n is equal to x of n by 2 plus x conjugate of n minus small n mod capital N by 2. Okay. Now what we have to evaluate is what is this number. Because x of n we know, but what is this number? Now, what is x of n? Go back to the question again. 4 into delta of n, that is at n is equal to 0, you have 4. At n equal to 1, you have 3. At n equal to 2, you have 2. At n equal to 3, you have 1. Right? That's how the impulse functions are. Right? Fine. That's what I'm going to compactly write it as. X of n is same as 4, 3, 2, 1 with an arrow mark at 4, indicating that x of 0 is equal to 4. Therefore, what is y of let this number, this x conjugate of n minus n mod n be y of n. Therefore, what is y of 0? Y of 0 is same as x conjugate of 6 mod 6, because the small n is 0. Y of 0 means. Therefore, 6x conjugate of 6 mod 6 is nothing but 6 mod 6 is 0. Therefore, x conjugate of 0, which is equal to 4. Because I'm taking 4 and then 2 conjugate, it becomes just 4. Similarly, y of 1 is x conjugate of 6 minus 1, that is 5 mod 6, which is x conjugate of 5. So what is x conjugate of 5? 0, 0, 1, 2, 3, 4, 5. So 0. So 0 conjugate is nothing but 0 only. Similarly, y of 2 is x conjugate of 6 minus 2, which is 4 mod 6, which is nothing but x conjugate of 4, which is again 0. So 0 conjugate is again equal to 0. Then y of 3, which is nothing but x conjugate of 3 mod 6, which is nothing but x conjugate of 3. What is x conjugate of 3? 1 conjugate, which is equal to 1 only, because it's a real number. Again, y of 4 is similarly y of 4 equal to x conjugate of 2, which is equal to 2. And y of 5 is equal to x conjugate of 1 equal to 3. Therefore, your y of n, that is x conjugate of n minus n mod n, is nothing but this order. 4, 0, 0, 1, 2, 3 with an arrow mark at 4. Until this point, is it clear? Very good. That's all we have now found. Now we know W of n is nothing but x of n by 2 plus x conjugate of n minus n mod n by 2. That's all. We have both the signals. So this is basically x of n by 2 plus, this is the second signal we just found, x conjugate of n minus n mod n. That is basically this guy. So add both of them and divide by 2. So 4 plus 4 by 2 is again 4. Okay. Similarly, 3 plus 0 by 2 is 3 by 2. 2 plus 0 by 2 is again 1. 1 plus 1 by 2 is again 1. 0 plus 2 by 2 is again 1. 0 plus 3 by 2 is again 3 by 2. Okay. So with an arrow mark at 4. Therefore, your W of n is equal to this is a sequence W of n. A 6-point W of n. Is the answer clear? Okay, great. Let's do the next question, which is again an interesting question actually. Let the 8-point sequence x of n have the DFT. So they are giving you DFT sequence. X of k is equal to k plus 1, where k ranges from 0 to 7. I think it's one of the gate questions, I guess. This is also one of the gate questions. So x of k is k plus 1, where k ranges from 0 to 7. The question is, find the value of sum n is equal to 0 to 3 x of 2n. So what is this summation? Put n is equal to 0, you'll get x of 0. N equal to 1, you get x of 2. N equal to 3, 2, you'll get x of 4. N equals 3, you'll get x of 6, and you need to sum all of them. So essentially, you need to find the values of x of 0 plus x of 2 plus x of 4 plus x of 6. Fine? Fine. Let's see how to do this. What is the definition of 8-point DFT? X of k is equal to summation n is equal to 0 to n minus 1 x of n into twiddle factor at n equal to 8 power kn. That's a definition of DFT, right? Now I'm going to apply a nice trick, namely that x of 0, that is, I'm evaluating the at k equal to 0. That means what? This put k equal to 0 here. That means twiddle factor anything power 0 is equal to 1. Therefore, it just becomes summation over xn. Do you agree? So your frequency at k equal to 0 is just summation over all the time domain samples. Now, I will evaluate x of 4. Okay, that is nothing but x of 4 is nothing but summation over x of n into twiddle factor power 4n. But what is this twiddle factor power 4n? You see, W8 power 4n is nothing but e power minus j2 pi by 8 into 4n. That's basically the definition. But what happens is that this 4 into 2 is 8, and that will cancel with denominator 8. So it's nothing but e power minus j pi n. But e power minus j pi is minus 1, so it's minus 1 power n. Therefore, this W8 4n is nothing but minus 1 power n. Therefore, your frequency domain x of 4 is nothing but summation n is equal to 0 to n minus 1 minus 1 power n into x of n. Is this clear? Okay, great. Then now that's all. These are the two key observations. So what is x of 0? Sum over all x of n. That is x of 0 plus x of 1 plus x of 2 plus x of 3 plus x of until so on till x of 7, because it's an 8-point DFT. You see, it's 8 point. So you'll have till x of 7. Similarly, if you compute x of 4, okay, what will happen is that x of 0 is same, but x of 1 will be minus, because the minus 1 power n. Therefore, second term will be minus x of 1. Third term will be plus x of 2. Then you'll have minus x of 3 again. That is minus x of 3. Like that, you will have odd terms. Every alternative term will have a negative term. This is basically your capital X of 4. Now, basically, when I add both these equations, this x of 1, x of 3, x of 5, and x of 7 they will basically get cancelled. But x of 0, x of 2, x of 4, x of 6, they will get added 2 times. So capital X of 0 plus capital X of 4 is nothing but 2 times small x of 0 plus small x of 2 plus small x of 4 plus small x of 6. Or this summation is nothing but x of 0 plus x of 4 divided by 2. But what is the left hand side? What is asked in the question? You see, our question is exactly to find sum over all the time domain signals at even time instances. That's what we found the expression for also. It is just nothing but capital X of 0 plus capital X of 4 divided by 2. But what is capital X of k? Something but k plus 1. That's a given question. Therefore, x of 0 is nothing but 0 plus 1, 1. X of 4 is nothing but 4 plus 1, 5. So 1 plus 5 by 2 is nothing but 6 by 2 equal to 3. Therefore, the given answer is the answer for the given question is 3. Is it clear? Great. So the next question, okay, I wrote 10th question. Let me see if it is really 10th. This 7th, 5th, 4th, 3rd, 2nd. Okay, that is the 9th question, not the 10th. The next question is basically the 9th question. Okay. It's again a good question, which can be a potential good question for gate. The question is as follows: x of n is a discrete time domain signal given by delta of n plus 2 into delta of n minus 2 plus delta of n minus 3. Simple. what is the 4-point DFT of x of n? Second question is, let y of n be a 4-point circular convolution of x of n with itself. Then what is y of n? What is the 4-point DFT of y of k? Okay, these are a two-part question. We'll answer one by one. First, the question is, what is the 4-point DFT of x of n? Fine. Now, you see delta, what is x of n? Delta of n is nothing, delta of n plus 2 into delta of n minus 2 plus 3 into plus delta of n minus 3. Just apply the time shifting property of Fourier DFT. So delta of n is nothing but it's just 1. That's what we saw in question number 3, right? You go back to this question, you will know. Delta of n, yeah, here. Okay, maybe here. So delta of n has the Fourier transform 1. And delta of n minus n naught has the DFT twiddle factor power n naught k, where n naught is the amount, the number of samples by which you delay or advance. That is n minus n naught, right? This n naught is basically going to come over the power of twiddle factor. That's what we saw in the question. Just apply this time shifting property. So delta of n will have the DFT 1. 2 into delta of n minus 2 will have the DFT 2 into twiddle factor W4 power 2k. Why 4? Because we are asked 4-point DFT. Therefore, W4, that is the twiddle factor of order 4, power 2k. 2 is basically your n naught. Fine. Similarly, delta of n minus 3. So it is twiddle factor W4 power 3k because n naught is equal to 3. Okay, is it clear? Therefore, your x of k equals to 1 plus 2 into twiddle factor power 2k plus twiddle factor power 3k. That's all. This is the DFT, 4-point DFT of x of n. Now, second point is find the value y of n, which is a circular convolution of x of n with itself. Okay, that is, and find the 4-point DFT. We will first find the 4-point DFT of y of k, and then take the inverse DFT of y of k to find y of n. Okay, apply convolution property. So basically, if y of n is equal to circular convolution of x of n and x of n, then y of k must be product of x of k with itself, right? That is x of k whole square. That's a circular convolution property of DFT. We know x of k already from the first part. Therefore, it is nothing but 1 plus 2w4 power 2k plus w4 power 3k the whole square. Now just do a plus b plus c the whole square, right? A square plus b square plus c square plus 2ab plus 2bc plus 2ca. And all these are twiddle factors. That is e power something, right? E power j something. So you apply the complex exponential property, do all these simplifications and verify that this is same as this number here. 5 plus 4 into w4 power k plus 5 into w4 power 2k plus 2 into w4 power 3k. You can show that, just do some algebraic simplification and show that this is equal to this. So we found the y of k, the y of k, that is the DFT of circular convolution of x of n with itself. Now what is the question? What is y of n? Take the inverse DFT of this guy. So this is nothing but 5 into 1. Therefore, this is nothing but 5 into delta of n. The inverse DFT of 5 is nothing but 5 into delta of n. 4 into w4 power k is nothing but it is k is nothing but k into 1. Therefore, you are only having one x in the exponent. That means you need to delay by 1 in the IDFT. Now w4 power 2k, which means you are delaying by 2. That means it should be 5 into delta of n minus 2. Similarly, when you have w4 power 3k, you're delaying by a factor of 3. Therefore, the IDFT of last term is 2 into delta of n minus 3. That's all. So basically, your inverse DFT of y of k is given by 5 into delta of n plus 4 into delta of n minus 1 plus 5 into delta of n minus 2 plus 2 into delta of n minus 3. Is it clear? Great. Fine, that's all I have for today. I think I have covered all the questions, but maybe I would have gone through slightly faster today, but all these notes will be posted to you, will be shared by NPTEL, so you can always read all these at your leisure. These notes are made available to you, all whatever I'm sharing discussing in the sessions. So feel free to go through them and ask me any doubts you may have. And that's it for today. And just a couple of announcements. Basically, next week we will not have a class on Friday, but we will have on Sunday. Okay, which is basically 12th April. Okay, so that's the first announcement. I will basically NPTEL will share you the updated this particular information, but the meeting link will remain the same. So it will be Sunday 6 p.m. Okay, that's the first announcement. And the second announcement is we will be having, so next session will be the last regular session, the 12th session of this TS session in this particular course. So apart from the 12th session, that is the next session, we will have one last session where we will quickly summarize the entire course and solve some gate problems. That will basically summarize the entire course. Okay, so we will have two more sessions. The next session will be last session on 12th April, and the last session will be on 16th April. The meeting link will be same, and that will be at 6 p.m. That is a Wednesday, on the week after the next week at 6 p.m. That will be the last final summary session for this course. Okay, so these are the two things. Please ensure to attend. Okay, so that's basically the two announcements that I wanted to make. Are there any questions for today? Okay, great. So then I think we can stop for today at this point. We can again continue. We can continue again next week, Sunday at 6 p.m. Same link. Okay. Yeah. Okay. Then see you next week. Thank you.